Greetings and welcome to another presentation in the series Aviation Safety Risk Management through Hazard Analysis. This presentation takes a look at fault trees and bow tie models. So let's jump in with both feet. Suppose we're interested in performing an aviation hazard analysis, and the one we're interested in is looking at the risk associated with the failure of an aircraft landing light. Well, to get there, we need to start off with a simple technique, and we'll start to build the complexity of it until we get to a point where we could actually perform this kind of risk assessment. So here's a starting point. Let's say that we have a very simple lighting system like the one you see drawn here with a switch, a battery, and a light. The idea being if we throw that switch, it completes the circuit and the light comes on if everything's working. What we need to do in order to proceed is we need to develop an architecture, some way of describing how this system is intended to work. Here's one way of doing that, and there are many different ways. There's no right or wrong way of doing it, but in this case what I've done is I've just represented the battery, the bulb, and the switch with some common symbols, and it communicates the idea of how this system is intended to work. The next step is to identify uncertainty. What could go wrong with this system? And what I'm going to do to identify uncertainty is I'm going to use circles or ovals to represent things that could go wrong in this system. And you can see the three things here. The battery fails, the bulb fails, or the switch fails. And this is essentially going to start to build the foundation that I need to develop a fault tree. But before we get to that, let's take a look at fault trees in a little more detail to understand what some of the common symbology looks like. Now, this is by no means a complete list, but these are the events that are most commonly seen in fault trees. And it starts with the one I just showed you, the basic event. And the idea here is that we have some function or some system component that we don't want to decompose any further because essentially we have what we need. So as an example, suppose my basic event represented the failure of a computer in some system. And I know what that probability is. I can just create a basic event for that. Now, if I really wanted to, I might be able to develop a fault tree just for that computer, and I could start to look at the individual reliability rates for the processor, the memory, the motherboard, and so on. But if I already know the top level probability and I don't feel like I need that level of decomposition, I can just represent it through this basic event. The other key idea here is that every basic event in our fault tree is going to require some piece of data, a probability of failure or fault. The next one down is the event, and this is also referred to as an intermediate event from time to time. It's represented by a rectangle, and this is essentially the opposite. This is the case where this event is going to be made up of some number of additional events below it. So there may be some basic events, there may be some other intermediate events that are going to be joined together by some gates. And we'll look at the gates in just a moment. The last event is a conditioned event. And what this is doing is, just as the name implies, it's applying some kind of condition. And what it's really telling us is that the data in the fault tree is conditioned upon whatever it is that's specified. So for instance, if we had a twin engine airplane like the one I showed a moment ago, each of those engines may have an alternator, and the probability of an electrical system failure in that aircraft is probably quite low. However, if we have to shut down one of those engines, and by doing that we lose one of those alternators, it probably changes the chance of losing power altogether because now we only have the one alternator left. So that might be a conditioned event. We may have a fault tree that's quantifying the probability of a total electrical failure in the aircraft, and we may want to condition it on the event of one engine shut down. Let's look at some of the gates now that we use. And the top two are by far the most common. The others are only used from time to time. The AND gate is indicating that event A and B must occur together. So as we'll see in a moment, suppose you had two independent power sources and either one of them was sufficient, like maybe two battery backup systems for a computer. In order to lose all of your power, you have to lose both of them. You have to lose A and B. And that's the idea behind an AND gate. Now an OR gate is just the opposite. Now we're talking about a system where losing one or the other, I guess, or both at the same time would represent failure of the system. So again, inside that computer, if we lose the processor or the memory, either one of those is probably sufficient to stop the computer from working. Now the exclusive OR is really a type of OR gate, but it has a unique characteristic to it, and this is going to influence the mathematics that are going on underneath this tree a little bit later. The idea is this: suppose we come to an intersection where you can go straight, left, or right, and the correct choice would be to go straight to get to your destination. Well, event A might be the event that you turned left, which would be a failure, or event B might be the event that you turned right, which would be a failure. And the idea here is if you turn left, you can't possibly turn right. Event A excludes event B, and that's what this gate is trying to capture. The transfer gate is really just administrative. If you develop a fault tree that's so big that it's not feasible to show it on one screen or one piece of paper, you can add these transfer gates that simply indicate where one tree connects to another. So let's build our first fault tree using that simple diagram that I presented earlier. I also developed the three uncertain events: the battery failure, the bulb failure, and the switch failure. And the key idea here is that in order for this system to fail, all I need is one of these three things to fail. In other words, I have to have all of them working in order for the system to function. So what I'm going to do is I'm going to add an OR gate, which says that if the battery fails, or the bulb fails, or the switch fails, any one of those events or any combination of those events will lead to a light system failure. And voila, we have our first fault tree. But now it's time to take a look at the math that goes with this tree. Now, never fear, because today there are applications that you can use to do all of this for you. And there's no reason today why everyone needs to understand the mathematics. But in case you come into a situation where you do need to understand, or you just want to appreciate what's going on under the hood, let's take 1 or 2 minutes here to just look at that. The Boolean algebra kind of looks like this. Let's start with an OR gate. If we have two events, A and B, joined by an OR gate, we're saying that either A or B or both could take down our system. This is the math that goes with that. We start off by adding A and B together, and then we subtract out the product of A and B. Here's why. Suppose we have two circles that represent the probability of A and of B, and they overlap. What this tells us is that A could happen, or B could happen, or they could both happen. And so what we're doing with that second term, by subtracting out the A and B, or the A times B, we're pulling out that center section, because if we simply add them together and don't do that, then we're double counting that shaded area. Here's what it looks like as an example. If A and B are both a 50-50 chance, we add them together, which would give us a 100% chance of failure, but then we subtract out the overlap, and we wind up saying there would be only a 75% chance of failure. The AND gate is much easier to understand. We just take event A and B, we multiply them together. And if we were to expand this idea and add an event C, it's easy. We just add another term in here. It would be A times B times C, and there's really no limit to how many events we could connect with an AND gate and just multiply them all together. Things get tricky though when we start to put multiple events together with an OR gate. Now we have A and B and C, and here's what the equation looks like. You can see it's grown in complexity quite a bit compared to the others. What we're doing is we're starting off by adding the three together as we did before, and we're subtracting those overlaps of A and B, of B and C, and of A and C. But then what we need to do is we need to pull out the triplicate. So here's another diagram like the first one, and you can see the same relationship that I showed on the left between A and B. There's the probability of A and the probability of B, and by subtracting out A times B, we've eliminated that football-shaped portion, just like you've seen on the left. But now what we've done is we've essentially over subtracted for this area in the center. So that final term in the equation is essentially adding this back in so that we have an accurate count of how much probability we're talking about. Here's an example. Again, everything's 50% chance, and you can see that in this case it would be a 87.5% chance of failure if that was true. All right, enough of the mathematics. Let's just see a practical example of how this is applied in our little light system. Again, just threw some easy to handle numbers at it, 0.1, 2, and 3. And this is what our equation looks like from the previous page. So if I just take those numbers and plug them into the equation, here's what it looks like. And then just running the numbers again, it leads us to something like this, 0.496. Probably not something you could do in your head, but again, no reason why you have to do this out manually. It's very easy to automate, even in a spreadsheet. All right, let's get back to our aircraft and the landing light. So we have to understand the architecture, and here's an example of something we might look at. And I realized that right off the bat, this is a little overwhelming to look at. And there's a lot of information in here, but we don't need all of this for our purposes. All we're really looking at is the landing light. And this is a picture of what one might look like. And specifically, I chose this picture because I wanted to show the possibility of having two redundant lights in this system where one or the other or both would be sufficient for us to get the light we need. In the diagram on the right, I've just sort of circled the area where we find the landing and taxi light, another name for this. Also, you can see that some power sources are in here. So here's an alternator, there's a switch, and a battery. And although it's a little bit of an oversimplification, I'm just going to focus on those components and show you how we can diagram these out and then how our fault tree changes. So here's another representation of that system. And the way I've tried to lay this out is to show the relationship between these different elements of the system. So we've got the battery and the alternator, and either one of those power sources is sufficient to illuminate these light bulbs. So if I've got the battery or I've got the alternator or I've got both, then I'm in business. I have to lose both of those at the same time in order to have a power failure. So here's what it looks like in a fault tree format. I've just listed my two different components there. The 28-volt battery fails or the alternator fails. And I've connected them with an AND gate. And what that is saying is in order to have a power failure, the battery and the alternator both have to fail. Exact same relationship exists with the bulb. Bulb 1 and bulb 2 both have to fail in order for me to lose all of my light bulbs. The switch is the same as it has been. If the switch fails, that'll take out my system. And the important thing to see now is that these three different components, if I lose any one of them, it will result in the system going down. So I'm going to join them together again with that OR gate to represent that relationship. All right, let's move on to see what a bow tie model looks like. So all I've done is I've taken that same fault tree that we just created, and what I want to do is go back to the very first presentation in this series where we introduced the idea of a risk framework. And this is what it looked like, just sort of a generic version of a risk framework. And what I can do now is you can see that on the far left, the column says hazard. In this case, the landing light system failure is the hazard we're interested in. So if I just sort of slide this down here, I can indicate which hazard it is that I'm going to perform my risk analysis on. Now, if I rotate the entire fault tree and just sort of set it on its side and then move it into position, and then I reconnect it, you can see now what we have is something that kind of takes on the shape of a bow tie. And this is where the name came from. Now, in practicality, we don't have to go through all this graphic maneuvering. And in most cases, what you find today, because of the nature of the automation tools we use, the fault trees will be done in one place using one type of software, or even in a spreadsheet, you may see the fault tree being done on one tab in a spreadsheet, whereas the risk framework will be in another tab, and then one will feed the other, just having some kind of a connection between the two. It doesn't have to be a graphic connection like the one you're seeing, but thought this might be helpful to explain what a bow tie model is and where the term came from. Before I go, I want to leave you with some references. And in my experience, one of the best agencies in the government at managing safety risk is the Nuclear Regulatory Commission. And there's a good reason for that. 3 Mile Island. In the wake of that accident, the Nuclear Regulatory Commission had to take a hard look at their practices, which at that time in the mid 70s were very qualitative approaches and some things that had been developed from the 40s to the 70s. And quite frankly, they weren't working. And that became evident. It was one of the things that came out of the 3 Mile Island accident. Here's a screenshot from the Nuclear Regulatory Commission's website. It's publicly facing, and you can get to this if you'd like. But you can see they're communicating the same idea that we just looked at. They've got an event tree, which is their risk framework, and they're using a fault tree to come up with a probability that's going to feed into that framework. And that's what they're discussing here. The Nuclear Regulatory Commission's Fault Tree Handbook is hands down the best reference that I've ever come across to explain not only what a fault tree is and how it works, but also the theory behind it. It's exceptionally well written. And one of the things that I think I like the most about it is it was written and published back in 1981. And if you search for this online, you may even find a version that was typewritten on a typewriter, and you'll even find some hand-drawn graphics in it. So thinking back to what the world was like back in 1981, this is really a tremendous accomplishment for that time. And it's still, as I said, today, the best reference out there, in my opinion, to explain fault trees. And if you want to get into fault trees in much more detail than I've had a chance to go over in 10 or 15 minutes, this is the place that I would turn to first. Another outstanding reference is the NASA Fault Tree Handbook, which was written about 20 years later. And you'll see a lot of references to the Nuclear Regulatory Commission's work in this Fault Tree Handbook. But again, another exceptionally well-written handbook, and one that if you really want to get into the nuts and bolts of fault trees, it's a good place to turn. That's all I have for you in this presentation. I hope the information is useful to you. If it was and you made it this far, I hope you'll throw out a like or maybe subscribe to the channel, and I hope to see you in another video soon.